So we switch to English. So it's a pleasure to have Professor Anderson Janotti with us today. Professor Janotti got his bachelor's at USP, São Paulo in 1995. His PhD also at USP in 2000. Then he spent a few years in Colorado and Oak Ridge doing postdocs. And then he was a staff researcher at Santa Barbara in California. And since 2015, he has been at the University of Delaware, where he's now a full professor. And Professor Janotti today is going to talk to us about the discovery and characterization of quantum materials through computation. Professor Janotti, thank you very much for accepting our invitation. The microphone is yours.
Okay, George, should I speak in English or in Portuguese?
Bon. Sorry, in English, please.
In English.
Thank you. Yeah, thank you.
I would say that after some time away from Brazil, right, the English stops improving and the Portuguese gets bad. So it doesn't sum to one anyway. But anyway, let's see. So first, just an advertisement here that we are organizing the ICDS is a 32nd edition of this international conference on defects in semiconductors. They'll be in Delaware, and there's a great list of plenary speakers and invited speakers. So if some of you are interested in this area, although we have a list of invited speakers, some of the contributed talks will be upgraded to invited talks. So just to be aware, and just contact me in my email, and I'll be happy to send you the information. So the title of my talk was quite general. Usually we do that because the talk is far away, and we think, okay, at that point I'm going to make it more specific. But what the idea is discovery and characterization, yes, through computation and quantum materials, because many of the effects that we deal with we cannot describe using classical physics. But more specifically, I will talk about rare earth and pnictide nanostructures. And that includes nanoparticles or embedded nanoparticles in semiconductors, and also thin films. And there are some cases here that we see a transition from trivial semi-metal to a topological phase. And the discovery is this transition from trivial to topological, but the characterization is actually, there are a lot of experimental data on these nanoparticles and very little theory on that. And we started making progress on that. So the first question they ask me when I go and start talking is, where is Delaware? So that's the map of United States, and you can see Delaware here, very close to, actually making borders with Pennsylvania, New Jersey, and Maryland. It's a very small state, but there's a lot of fun. So the University of Delaware is the only one research university in Delaware. Here's a view of a part of the campus. There is this old style, but actually the building is actually not that old. A lot of things to do in Delaware. They have brewing companies. The beach is very popular in Delaware because people from Pennsylvania, Washington, D.C., they end up going to the beach in Delaware. And a lot of state parks, actually. And This is our department. So I mean the Department of Material Science and Engineering, divided in soft and hard material science. This is the faculty. We have many centers associated with the department, funded by the Department of Energy, by the NSF. And these are just two examples. The MERSAC, which is a multi-million-dollar award involving many faculty in the department. And we accommodate many students under this grant. This EFRC is funded by the Department of Energy, deals with specific in plastics. Also the NRT, involving data science training and materials innovation. We have state-of-the-art facilities. This has a clean room, has state-of-the-art rooms for microscopes. We also have a materials grow facility with a few MBE machines. And that's my advertisement. But let me say, if you know any student, or if you are a student interested in doing PhD in the abroad, right, in US, talk to us. We offer full tuition and stipend. So basically you have a scholarship. You paid to do your PhD, much like in Brazil when you have a bolsa da FAPESP or CNPq. So you fully covered in that sense. So this is my research group. A few years ago, actually, I'm listing here some of the students and postdocs left the group already. In the collaboration, I'm underlining here the people that are involved in this particular work. Garnett Bryan from NIST, the theoretician, and then from Santa Barbara, there's Chris Palmstrom leading the MBE group, and Hadass is one of the students, and Shovik Chatterjee is a postdoc that is now in India. My group, we try to be broad in the sense of methods and applications, right? The main thing that in general, the general topic is electronic structure theory, methods that are first principles that you only need the atomic numbers in principle. And this is based on density functional theory. We go a little beyond the standard approximation doing hybrid functionals. And in some cases, we go beyond, we calculate the quasi-particle energies using the GW approximation. Another way of, another direction is what we call DFTB, which is an approximation to DFTB. To DFT, there's a tight binding underlying that approximation. And sometimes we resort to empirical potentials, not often. And more recently, we started looking at quantum Monte Carlo methods in collaboration with Argonne for some specific problems. Particularly quantum Monte Carlo is a very expensive computationally, much more than the other methods that we have been dealing with, and then we still in the learning stage. In general, for the funding agencies, we sell it as we are working on sustainable energy, environmental materials, solar cells, photoelectrochemical cells, materials for energy efficiency, such as high power electronics for energy conversion. In more advanced, it will be quantum computing and quantum communication. That basically defects that act as qubits or two-level systems in some insulators that can be detrimental to superconducting qubits, and also single photo emitters. So the materials that we deal with, because the nature of the problem, right? Our lab is essentially covers the periodic table right? So we deal with wide and narrow gap semiconductors, semi-metals, magnetic materials. More recently, we have been working on these outer magnetic materials that shows very interesting spin splitting without even need of spin orbit, topological insulators, semi-metals, and two-dimensional materials. Properties that you usually look at, well, what is the impact of defects? We have been looking at nanoparticles, properties of interfaces and surfaces, surface reconstructions, surface energies, and what we usually look at is defected transition levels, ionization energies. We have been calculating absorption and luminescence spectrum associated with the defects. Heterostructures and band alignments. Most of the devices that are made are based on heterostructures. Very few deal with a single material. And you needed to know how the bands align at the interface, and so on. So the core, so first principles means we start from the basic quantum mechanics equation, right? And it's easy to write. You can just use a page, you can write it down. However, you cannot solve it that easily, and especially because of the electron-electron interaction, the term here in the middle. And you can say, well, if you try to solve brute force by in a numerical way, right, or on a grid, right, you realize that to describe 5 electrons on a 10 by 10 by 10 grid would require 10 petabytes. So you cannot do that. So you need either an approximation or a different route, right, than the brute force approach. So the most popular now is to use the density functional theory, which basically maps the many-body problem into one electron problem, moving in an effective potential that depends only on the density. So the total energy is written as a function of the electron density. There's a kinetic energy term, a Hartree term, a Coulomb, that's the Coulomb term, and the exchange correlation. And the idea then that the density is written as a sum of single particle densities, single electron densities, right? And you end up with an equation that is very similar to the original Schrödinger equation. The problem is that the exchange correlation, we still don't know the form, the analytical form, and it has to be approximated. The most known approximation is the local density approximation, where the exchange correlation functional is modeled based on a uniform electron gas. And then you can actually solve the problem using quantum Monte Carlo method for a wide range of densities and basically parameterize it and have a sort of either a analytical or a numerical form for this exchange correlation. And this was many years ago, and then came corrections to that. The most straightforward correction is to add gradient of the charge density, and this is what we call the generalized gradient approximation, or GGA. And that's what made it popular among not only in material science, but also in chemistry, and it's nowadays widely used. So there are many different functionals available, from LDA, GGA, meta GGAs. And one of the problems in the case of semiconductors and insulators is that the gap is not well described. If you think that, well, what is the energy of adding or removing an electron, you're going to get about half of the experimental data, or value, essentially. There are ways around it. They are not that old, but not that new as well. The hybrid functionals that mix two theories, the Hartree-Fock and DFT, essentially corrects part of that problem, which essentially is the electron self-interaction in the LDA or GGA. So when you correct it by writing your exchange in a Fock exchange form, part of the self-interaction is gone, and the gap can be actually described quite reasonable compared to experimental data. And of course, the formal way of describing adding or removing an electron is the quasi-particle GW. But these are much more computationally expensive, and we are still learning how to do that in terms of forces and geometry or atomic relaxations. So that's the background. That's more or less what we use. Of course, what I think cannot just stop here and say, yeah, okay, that's but actually there is a development beyond, and the way we engineer our calculations to describe different systems like interfaces or surfaces and so on. We always take advantage of, let's say, numerically in terms of a fast Fourier transform. So and this is, I think, we know this way before, right? For instance, in a crystalline solid, we take advantage of this periodic. We use these periodic boundary conditions that are based on the translational invariance. So your wave function has a form, that's the block wave function, right? Form, and the states are labeled by the block wave vector and the band index n, essentially. The block vector is constrained within the first Brillouin zone of the reciprocal lattice, and the band index is an integer, right? That basically is of the order of the number of electrons in the unit cell. But given that, we can actually write wave functions in plane waves, in terms of plane wave, expand that in plane waves, and actually that allows a systematic convergence criteria. Basically, you add the more basic, more plane waves, you get the results are better converged in terms of expanding charge densities and potentials and so on. And this is now well established and actually is very suitable. So essentially, you transform the problem of solving a differential equation in real space to solving a set of linear algebra equations for the coefficients of the plane wave expansion, essentially. And this is very suitable nowadays for parallelization in CPUs and GPUs, right? So this is the basic scheme for, so the solutions they have to be, they are solved in this self-consistent manner, because if you look back at the equations, your Hartree potential and your exchange correlation depends on the solution, on the density. So you need a initial guess for your density that you define the potential, and you can then calculate the Hartree and the exchange correlation potential, putting as an effective potential, solve the equation, and get another density. And then you follow this loop until you converge on the density, or you look at the total energy. When the total energy doesn't change anymore, you say, okay, it's converged. Well, because these plane waves are very convenient for systems that are periodically repeated, it doesn't mean that we can only deal with crystalline solid, perfect crystalline solids. We actually can use that. We can be creative and use that to study pointed defects, molecules, just placing a molecule in a very large box that defines with a large lattice vectors that define your cell, your unit cell. We can study interfaces, surfaces, using periodic boundary conditions in 3D. This is our lab. It's interesting when, whenever you have experimentalists visiting and everybody, they, in the department, they proudly show their lab, or whenever you have a visitor, right? We don't have that, right? I cannot show my lab essentially because we only use the computers to connect it to these larger computers. So we have access to NSF. Actually, Stampede is a DOE. No, Stampede is NSF. And the Permuter is the new computer that's really, really fast from the Department of Energy. And we have our small one. It's not actually this size. The diving at UD is much larger than that. I think it is the initial modules, but it's not as big as compared to the DOE computers or the ones in Texas. So let me start trying to describe these rare earth pnictides. And I'll try to tell you why we are interested in that. So the work here has been done by Ricky, who she's the student involved in these calculations that I'm going to talk about here. Just to remind you what are the rare earth. The rare earth is this column here highlighted from lanthanum to lutetium. And they are basically the ones that have either no F electrons from the case of lanthanum, or completely filled F electrons in the case of lutetium. The pnictides are the column 5 here on the left. And I was not sure if nitrogen is called a pnictide, but phosphorus and arsenic, antimony, and bismuth, so they are part of this family. So we are looking at a very simple compounds formed by these two set of elements. So I think the most one of the simplest crystal structure we learn in solid state physics is the rock salt, and these rare earth pnictides, they actually they assume they are stable in this rock salt crystal structure on the left side here. And in the middle is a typical band structure. So 0 is our Fermi level. You see here the Fermi level crossing two bands. These bands, they overlap in energy, but actually they don't overlap in k-space, right? So you always have, for a given k, you always have, let me see, no, yeah. Well, okay, we can discuss that later. But essentially, so these are semi-metal because you have electron pockets centered at the X point. In the X point, if you know your solid state physics, you see that in this is an FCC lattice, underlying lattice. So your Brillouin zone is this figure on the right. And the X point are at the edge, actually at the center of the square faces. Okay, so you have a X1, X2, X3. So this is the Fermi surface, right? So these pockets, they form these ellipsoids. So from X to W is actually going perpendicular from X3 to one of the edge, the corner of the square face, essentially. So that forms these ellipsoids. So this is the electron pockets. So and the whole pockets are centered at gamma. So you see they are the top of the what we would call the valence band at gamma would composed mostly of the pnictide p states of valence orbitals, right? And they are split because of the spin-out splitting in 2+1 band. Right, and I didn't say that, but the electron band, it comes from the rare earth d orbitals. Okay. So that leads to low carrier concentrations, relatively low carrier concentration. If you compare, for instance, with copper, where you have 1 electron per atom in the unit cell, that will be 2 orders of magnitude less than that. So that's why they're called semi-metal, right? And one interesting characteristic is that it's fully compensated. So the number of electrons equal the number of holes if you don't perturb the system, right? And even sometimes you can perturb it a lot, but they still satisfy this condition. What is interesting here is that this material is actually fully compatible with the 3-5 semiconductors. So let me, often when you started describing this, the first thing people ask is say, wow, so how do you deal with the F electrons, right? And here are band structures we took gadolinium, which it has 7 F electrons, each gadolinium. So you have a half occupied F bands. And erbium is not too far from gadolinium, but to the left a little bit. And lutetium is fully occupied F bands. If you look at these about -8 electron volt in the case of gadolinium compounds, these thick line, basically they are all the occupied F bands. The unoccupied ones are about the 4 electron volts, centered at the 4 electron volts above the Fermi level, right? In the case of gadolinium, arsenide, antimonide, or bismuth. In the case of erbium, there is a splitting, right? So we are not trying to compute here excited states. We are looking only at the ground state, trying to make sure we don't have problem with correlation or multiplex. And in the case of lutetium, it's easy because it's fully occupied. You can see that the 2 lines at -8 electron volt, they are fully occupied, and there are no F electrons near the Fermi level. So I want to point out this interesting crossing here in the case of bismuth, where the lanthanum, the rare earth D bands cross the pnictide P bands, and that actually is an interesting crossing that makes some of these materials topological semimetals due to this crossing. But the Dirac point is well below the Fermi level. It's harder to assess it, right? Even with the spectroscopy methods. So these 4F flat bands are far enough from the Fermi level and localized enough that we are going to consider them as core states for now. Okay. So this is a close comparison of our calculations of erbium arsenide, because that is the material we are going to talk about, the nanoparticles. And I'm showing the case on the left with 4 F electrons, and the case on the right without F electrons. And you see that the expression of the bands do not change much, and there's some extra splittings when you due to the F interaction, unoccupied F with the pnictide P, but these for us, we are going to neglect that. And so we are going to talk about only for systems so far in this problem with, we are not going to take the 4 F electrons into account. So,
Anderson, may I ask a question?
Yeah.
Yeah, so there is no magnetism coming from the 4F electrons?
Well, in reality, there is, right? So
there is.
In reality, so this material is antiferromagnetic.
Okay.
But this is up to 3 Kelvin. After that is paramagnetic.
Okay, and the mechanism is RKKY?
I suppose so.
Okay, thank you.
So, as I said before, these rare earth pnictides, they are compatible with 3-5 semiconductors. Early on, at Bell Core, right, at Bell Labs, a spin-off Bellcore was a spin-off of Bell Labs. They were able to grow these erbium arsenide on gallium arsenide long time ago. And the idea that, well, it's a way to make a perfect contact. If you look at this image, this scanning electron microscopy image, so it's a cross section, right? It's not the surface, it's a cross section. And it shows a very sharp, abrupt interface between erbium arsenide and gallium arsenide. And at the beginning, they thought, wow, I can make a perfect contact where there's no roughness, no defects, right? What we learn from this interface is from this image is the structure of the interface. If you look at these, let me see. If you look at the blue sublattice, is continuous. So you have a gallium arsenide, yellow at the bottom, and then erbium arsenide at the top. And the blue atoms, they basically form a continuous sublattice. Right? It's just the rare earth that assume these different positions than the gallium underneath. Okay, and that was an interesting, and there was some questions after that, and not only they could make a very high quality thin film, they could actually make nanoparticles embedded in this 3-5 matrix. These are some of the pictures associated with that. And you see here, these nanoparticles, they have a size of around 1 or 2 nanometers. And what was interesting at that time, I think one of the things that caught attention at that time was perhaps that could be a good thermoelectric material, because the particles, they could scatter phono, but you still have a high conductivity due to having a 3-5 matrix like gallium arsenide with a high mobility electrons. And then the ZT will be essentially very high, right? And that partially true, but actually didn't happen, right? But they can controllably do this growth, right? So you have to be careful, because we are looking along 110 direction here, right? And I'm going to show some of the details. So here is the STS. So it's a scanning tunneling spectroscopy, but they did at the surface, particles at the surface, trying to probe the electronic structure of this composite system. And what they find is that whenever they are close to the on top of the erbium arsenide particle, you see more or less a dip near the middle of the gap of the semiconductor. But that's the only indirect way, and you don't know if the embedded particle would behave the same way, right? So there was a question: what is the electronic structure of the composite system? You have a semi-metal, but you make a very, very small particles, right? There was a question about, well, can the semi-metal become a semiconductor due to the quantum confinement? That was also tried to address that. But essentially, the information that we have from experiments are only indirect. Here in Delaware, we are very much interested in materials for terahertz generation detection. This is part of our MERSAC. And one of the ways we are pursuing is using photoconductive switch as a terahertz source detector. And these are based on materials that have specific characteristics, such as you create electron hole pairs that have a very short lifetime, so they recombine quickly, but they also very fast, they can move very fast, but also resistive, very resistive at low temperature, because you want to reduce your noise. And the idea then is to use these composite system, which is nanoparticles embedded in a 3-5 semiconductor. the good thing about the 3.5 that you can control the gap by alloying, and you can control more or less the carrier distance, so you can tune the optical pump wavelength, right? And the nanoparticles then would provide deep states that will give you short carrier lifetime and high dark resistance that are needed for you to build this terahertz source and detector. Now, what is the structure of this part? What is the detail of the interface? And what is the electronic structure? So we know very little about that. So here are ball stick modules tentatively built on these TEM images. You can actually mix the rare earth atoms. You can mix, for instance, terbium with erbium, and you still have these nicely separated and uniform size nanoparticles. And here are basically next to it are these ball stick models that were built based on this. But so we started looking to this and tried to say, well, can we actually do something? Can we understand this? Can we compute it? And the idea was, well, perhaps we can do a tie binding model first, but parameterizing a tie binding is not easy, especially because you have not only gallium, arsenide, but you have these d electrons from erbium, and that's kind of a nightmare. So we decided to use a brute force approach, and just to see how far we can push with these DFT calculations. Of course, we cannot. For the band gap, we use what is called this meta GGA from Beck and Johnson that give you a decent band structure. But all the structural optimizations were done with the GGA functional. But this meta GGA, this MBJ, is very close to what the hybrid functional would give us. If you compare, for instance, the dashed lines are the PB sol band structure for aluminum arsenide, gallium arsenide, indium arsenide. You see that GGA basically makes indium arsenide a semi-metal, right? It closes the gap. But the MBJ in red is very close to what we compute using a hybrid functional. And you see that we can even describe these semi-metals with these functionals, right? You see on the far right, the band structure of erbium arsenide with and without, by meta GGA in red and hybrid functional in blue. I have to say that if you try to compute you can compute the carrier concentration based on GGA band structure, you overestimated the overlap between the electron pocket and the hole pocket and give you carrier densities that are larger by a factor of 3 or 4 compared to the experimental data. So hybrid functional and these meta GGA give you a decent description of these systems separately. So we started putting them together. We first look, well, what is the energetics, right, of the particles, considering more or less same particle size, but different shapes. So we started looking from cubic and started cutting corners until we get spherical, using a fixed, very large matrix, a supercell as a matrix. And we find that the formation energy per erbium, right, decreases as you go from cubic to spherical. So essentially, the system prefers a spherical nanoparticles, also give us lowest density of the matrix plus nanoparticle system. And I think these actually is consistent with the experimental data, where they see more or less spherical shapes, but experimentally they say that they can also actually push and see some elongated particles as well. We didn't consider that here. How about size? So we took the same matrix and started changing size, and we go from 1.15 nanometer for the diameter, 1.73, 2.31, for the same material, and then basically just changing the particle size, and we find an interesting behavior. First, it may depend on the arsenic-rich or gallium-rich condition. So it depends on the chemical potentials. If you look at the formation energies here, right, the expression on the top, you depend on the chemical potential of the column 5, the pnictide, as well as on in the rare earth as well. But what we find is this interesting plot. So if you look at 1.15, the width of this square is basically going from arsenic-rich to gallium-rich. But then when you increase the particle size, you see the formation decrease, but then it increases a little bit, right? And we think the minimum may be in between. This is, I think, clear in the case of aluminum arsenide. I think the results are the minimum seems to be in this range, right? And doing anything in between may be difficult, right? Because any extra layer that you add, you deform the shape of the particle. Here we kept the same shape. And then we look at how the electronic structure of the composite system compared to the parent compound, essentially where's the Fermi level. And you see that for the ones that they are most stable, right, the Fermi level in the case of gallium arsenide end up in the middle of the gap. It's about 0.84 above the valence band, right? As you increase the particle size, the Fermi levels start coming down. But energetically, that will be more or less in the middle of the gap. In the case of gallium arsenide, also perhaps close to the middle of the gap in the case of aluminum arsenide. And we found that changing the matrix, you need, and keeping the particle the same, you end up with Fermi level at more or less the same energy if you take the band alignment of the different 3-5 materials into account. So it's more or less spin in an absolute energy scale, you can say that, right? It is interesting because you want to design terahertz materials where they are semi-insulating. So you want the Fermi level in the middle of the gap. But you also wanted to tune your laser for the excitation, right, to be closer to a common laser. So, for instance, if you go from gallium arsenide to indium gallium arsenide, now your conduction band, your Fermi level is spinning very close to the conduction band. It may be a problem because then you don't have a highly resistive composite material, but it will be highly conducting, and that will not work as a terahertz material. So we have to play with these, perhaps adding another element, and we are working on that, like bismuth, a little bit of bismuth, change the electronic structure of 3-5s, and what will be the best material for these terahertz switches, so that we are looking at. So this is what we did, and then I have I think 10 minutes to go through this, and we started looking at, well, can you make these materials, the rare earth, a semiconductor by making it very thin? The idea at the beginning was, well, the quantum confinement would lift the valence band, the conduction band, and lower the valence band would make it a semiconductor. That was the idea. But then we're looking carefully, we say, well, it doesn't really happen. You can say you always be a metallic system unless you go to very, very thin films. And I'm going to sort of describe here quickly in maybe 5 minutes, right? So these are compensated semi-metals, right? They are used for spintronics, thermoelectric materials, resistant contact materials, and so on. And they also show these extreme large magnetic resistance. And the question is, well, some of them are trivial or not. Often they talk about the overlapping between the electron pocket and the hole pocket X point, right? These are very small energy difference. Some materials, they show that the lanthanum antimonide is very close to that, but it's still a trivial semi-matter. So if you try to make a very thin film, you have to change. We are talking about the 001 direction here, okay? Not the 111 or any other direction, not the, and you have a tetragonal cell as a basis, right? But then when you look at the band structure of the tetragonal cell, you see that there is a pocket projected at gamma. These on the right side of this figure, right? This pocket comes from a projection from the X3, the pocket along with the Z direction that end up at gamma. And depending, when you make a very thin film, the pocket, so the M bar here is the projection of X1 and X2 essentially in the plane. The X3 is projected into gamma bar, and that's an interesting, let's say, behavior when you make it very thin. So this shows the sort of charge density square or wave function if you look at gamma. Actually, we're not, yeah, of these three, the three whole, let's say, the three pockets at X points, okay? So X1, X2, X3 is not the gamma then. But what you see is that the X1, they have wave functions that are distributed perpendicular to the confinement direction. So X1 and X2, they actually will suffer with quantum confinement, but X3, the charge density is actually distributed in the planes. So you can make a very thin film and the bands associated with X3 will not move. Indeed, that's what we find. So you look at this slab, did a freestanding slab with 15 monolayers thick, and you see that the X3 that is folded at gamma, you have many subbands due to many layers you have, and the bands at X1 and X2, they barely change it, but you can see them, they go up a little bit. And then the gap opens at the M bar, which is the projection of X1 and X2, right? But the bands at X3 that are project to gamma, they don't move. And then we say, okay, what happened when we make it smaller? And then you start to see, oh, there is a gap, actually. So you see your X1, X2 moving up and end up being above the Fermi level. And your bands that were overlapping at gamma, now they don't overlap anymore. Depending on the if you have odd or even number of layers, you can see a gap or not. And here is a zoom in the same region. You see two monolayers, you have a small gap, but three monolayers is a sizable gap. And then four and monolayers, there's no gap. At five, there is a gap. And then, of course, if you up to 7 monolayers, we see a sizable gap. And what happened is that this gap is due to spin-out coupling. If we don't add the spin-out coupling, they all cross. But if you add, you see anti-crossings, and because you have an inversion of bands at gamma. And once you get rid of many layers that end up in the energy region, these you end up with a favorable band inversion to make it a topological material. So we calculate the topological invariant for the 3 monolayers here. Also did it for 5. And basically, it makes the system a quantum spin Hall insulator. And this is the characterization of just looking more closely to this, what we did then. Okay, these are calculations for bulk materials. There is a gap. But if you wanted to see the topological states, that would be the edge stage of a very thin film. That means you wanted to make a nanoribbon. And this is a figure of the nanoribbon. My students always show that. I always complain about it because, well, it is repeated in the direction perpendicular to the figure here, right? So it's infinite if you look into the plane of the figure here. And the edges are the end of this. And he always, I think he suffers through this calculation because he had to go up to 50 monolayers to see the decoupling of the two edges so that he can actually see the crossing at gamma. The top view of this will be this, in this figure here. And these edge states are the ones that show up here. And then if you do a semi-infinite calculation, right, this spin resolved figure here clearly show these Dirac states in the gap of a sizable gap, I would say, right, 0.3 eV compared to what they have and they demonstrated for the first time is mercury cadmium telluride. This is probably the northern mine larger than what they had there. So these, you can ask, okay, what is the deal with the even or odd number of layers? And we went through that problem. And yeah, essentially it depends on the symmetry. You can say, well, 3 monolayers, you do have some sort of inversion symmetry. So 4 monolayers, you have a not inversion symmetry, you have a non-symmetric group. So it depends essentially on the irreducible representation of the bands that cross. So I will stop here. So first, I think this is the first time these electron structures of the nanoparticles have been reported. And so it's sort of prediction. We do see Fermi level pinning in the gap of the particles that are more stable in terms of size. And I think the calculations offer this design principle. If you want to change the 3-5 matrix, you can do that independently and not worry too much about the particle, right? So that I think is a nice thing to do. And in the case of films, right, we find that, well, the quantum confinement in films do not lead to a semiconductor state, but actually lead to a topologically non-trivial state with a sizable gap for the 3 monolayers law. Can that be done experimentally? Yes, it has been demonstrated in the case of gadolinium timonide on gallium timonide. However, they never probe, the spin resolved edge states of these particles. That would be interesting to check that. So the origin of this quantum spin Hall is really the SOC, the spin Hall coupling. And because you have a inversion of bands for the lanthanum D and antimonide B. It would be interesting to couple this with the magnetism of the other rare earth members, right? So far, we talk about the lanthanum, which doesn't have F electrons, right? But if you go to gadolinium, which is a F7, so it's almost an ideal system for Heisenberg. It doesn't have orbital moment. It's just a spin moment. Right? It will be interesting to see the coupling of the relation between these topological features that show up in the very thin film and the magnetism. So that is it. Happy to address any questions.
Anderson, thank you very much for this nice talk. We are open to questions now. Gerson, anyone in the room? Yeah, we have a question.
I have one here.
Okay.
Hi, Professor. In one of the first slides, you have shown the band structure with bismuth, I think, that you said that the crossings are topological crossings, but below for the Fermi level. Did you investigate this crossing? I think breaking time reversal symmetry So I think it's one possibility of biosemimetals. Did you investigate it? Or...
Yeah, this has been done by other groups in Germany. I think you're talking about the case of gadolinium bismuth, where these I highlighted this crossing here. Yes, this has been investigated from both the theory and experiment. The challenge is a semi-metal, and the weight on the surface state is sort of small, so it's hard to pinpoint the Dirac point, or harder to resolve. But this has been addressed both by theory and experiment. The bismuth especially. I think lanthanum bismuth is one, and gadolinium bismuth another one.
Okay. Any more?
Just, do you know how much below for energy level is discussed?
I don't remember. It's not that I'm saying that the Dirac point will be at the same energy. You would have to look at the electronic structure of the because this is a 3D, right? So you have to look at the surface of these materials. No, I don't remember. I remember seeing a lot of RP's data with not great resolution. That's how I remember seeing this.
Gerson, any more questions from the audience in the room? No. I have a question. I understand that you in the calculations you didn't consider these flat bands, but as there is a lot of interest now in flat bands because of these twisted bilayer graphene results that show strong correlations. Did you try to bring these flat bands closer to the Fermi level by using different pnictides or different rare earths? They always stay deep inside the core, or is there any possibility of bringing them closer to the Fermi energy?
Yeah, good point. I think we try to pick in this article that I have a reference somewhere here in this article. We try to pick the extremes, right? Completely filled and empty and in between. And okay. So far, what we have seen, the occupied states are very low in energy, let's say 5 eV, and the unoccupied are about 4 electron volt above the valence band. And this makes sense because it's associated with the large U value, right? So if you try to remove, you cost energy. If you try to add, you add it to a different orbital. And the U for these bands, it's probably around the 10 electron volts.
Okay.
So I'm not sure if looking at, let's say, cerium is complicated. I think neodymium may be. Yeah, that's what I would look at.
Okay.
One.
Interesting. There is a question here in the chat. You can read it. Can you see it in the chat? I have a question, actually a confirmation. When varying the number of layers, you did not use a DFT plus U approach, right? Just the hybrid functional.
Well, we did both. And we presented the results of GGA plus DFT plus U because we would like to, let's say, make sure we are well, it's robust against the functional, right? Essentially, this couple coming from a spin orbit, it may not change much if you do the calculation using a GGA functional. What may change is that, remember, you have to clear the gap, but there is a, let me show you here. you see these X1 and X2 pockets, the in-plane pockets.
Mm-hmm.
In GGA, the overlap of these pockets with the p-bands is large at the X point. And that means that you need a stronger confinement to lift it up, because you want to lift these guys, otherwise you always have a metallic system, right? And that in that case, as I said before, GGA always overestimate the overlap, and HSC give you bands and carrier concentrations that are closer to the experimental data. And that's why, yeah, that's perhaps one of the reasons we show these calculations with HSC, not the DFT plus one.
Okay. So have you tested the meta GGA functional there? That's another question from the same person.
No, we did. The calculation for meta GGA we did was only for the nanoparticles, right? So if you look at the electronic structure of the erbium arsenide with HSC and meta GGA in blue and red here, you can see they're almost on top of each other. So say, okay, that's a win. So we're okay with that. We can go on and put this material as a nanoparticle inside the 3-5 matrix. And the gallium arsenide is also well described with meta GGA, but we didn't try describing the thin films with meta GGA. We didn't.
Okay, so he says, thank you. Rafael Costa wants to ask a question.
Yeah, thank you, Professor Janotti, for the very nice talk. I have a question because I don't know jack about nanoparticles. It might be even a silly question, but what is the intuition behind the variation of your ground state energy with respect to the size of your nanoparticle? I know if it is large enough, it is bulk, of course, but how does that sweet spot arrive? I mean, is it due to surface tension or sphericity issues? I don't know. I was just curious about that.
Yeah, that is something we are we are writing the paper. So yeah, we are struggling to go through this. I suppose it has to do with the interface energy, right? Because you surface energy, interface energy versus bulk of the size of how many atoms in the bulk you have. So it's a combination of these two, right? I think this is but how to actually quantify it, that we are not sure how to do that. Yeah, that's how.
Okay. Okay. Any more questions? Anyone in the audience, Gerson? No. Okay. I had a question, but I think you showed the result with bismuth that has that Dirac point. Because bismuth has a very strong spin orbit coupling because it's the heaviest of the pnictides, is the lowest in the column. So that's probably why it shows more interesting results. The spin orbit coupling is stronger, maybe.
Oh yeah. Let's say, well, it has to do also with the position of the D bands, right, and the P band. Bismuth give you a P band that is higher in energy that will be closer to the D band. But then the lattice parameter also increase, right? When the lattice parameter increase, you see the dispersion of the D band also decreases, right? If you go from erbium arsenide, you see a dispersion here of the electron pocket, right? If you go to antimonide, the dispersion decreases. That means, well, there's a compromise between decreasing dispersion and increasing the position of the P p bands, the p bands, the pnictide p bands. So when you go to erbium bismuth, yes, they cross, but competition of these two things, right? Yes, the spin out is important. That's why you have a large splitting here of the bands as well at the X. But yeah.
Okay. Any more questions? Anyone? Not in the audience. If there are no questions, let's thank the speaker again. Thank you very much, Professor Janotti, for clapping the audience. So thank you very much. I'm gonna write you an email soon asking for the slides, if you don't mind. We're gonna post the video in our YouTube channel, and we'd like to have the slides available too, if possible.
Thank you. And please advertise. Anybody interested in applying for a PhD in Delaware, just talk to me. I'm not saying that you have to come here to work with me. The department large, there are a lot of opportunities, experimentalists, other types of theory as well.
Okay, thank you so much. We're gonna advertise.
Thank you.
Okay, thank you. And I will be contacting you for the slides either today or tomorrow.
Okay, thank you.
Okay, thank you. Bye.